We're going to spend a day looking at section 2.3, which is looking at polynomial functions and their graphs. So we've worked with polynomials quite a bit, but I'm going to give you kind of like the official little definition of it. It's kind of weird, and you don't necessarily have to write it down if you don't want to. We're just going to talk about it. So a polynomial. So the way we write a polynomial mathematically, if we're trying to give like a definition for it, we say f of x, which is telling us it's a function, equals, and we write it as a sub n, x to the n would be our first term, plus a sub n minus 1, x to the n minus 1. And we'd continue with like this type of notation until we got to like a1 n plus a sub 0, right? And you're like, what is all that craziness, right? So it's a good way, or it's how we write in mathematics. So we know that this is like our highest exponent. This is going down by 1, and it's going to continue to go down by 1 until you get to like the first degree. And then of course there is no x variable. That would be your constant term. All right. This a to the n out front would be your coefficient. This is like a different coefficient, that type of thing, all the way down until you get down to a single coefficient type thing. So, but what we need to know from this, or from any polynomial, is that our n, and where is our n? Our n is the exponent, yep. That our exponent always is going to be a positive integer. So if we want to look at the definition, or just in terms, right, all of our all of our exponents are going to be positive integers. And the numbers out front, so that a n and that like a n minus 1, all of those, which are we kind of call our coefficients, they are going to be real numbers. So they cannot be imaginary. Okay? And our an cannot equal 0, because if our an equaled 0, then it would kill our polynomial, or part of it in a sense, at least that first term, and we don't want that to be 0, right? We want that to be a real number. All right, so we need to find out if they are a polynomial or they are not a polynomial, right? So examples of polynomials. So we could have f of x equals negative 3x to the 5th plus the square root of 2 x squared plus 5. And we know this is a polynomial. If we go by our definition, if we go by our exponents are all positive integers. And then our coefficients are real numbers. So is negative 3 a real number? Yes. Is the square root of 2 a real number? It certainly is. Is 5 a real number? Yes, it is. And so we know that this, we could even say that this is a 5th degree polynomial. If we wanted to, okay, so it's got a degree of 5, right? What about g of x equals negative 3x to the 4th, then in parentheses I'm going to go with an x minus 2, and then another parentheses of x plus 3. We know this one's a polynomial, same thing. All of our integers, all of our exponents are positive integers, and our coefficients are real numbers. Can't really quite see it there, but it's right there, right? All real numbers. This one's a little tricky. What's its degree? So the degree goes by what the highest exponent is. So in this polynomial, I'm having a hard time. This polynomial is factored. But if we were to multiply this all out, like this x, you're going to multiply through by everything. So you would have like negative x to the 4th times this x, which would give you x to the 5th. And then you still have to multiply it by this, so it's actually x to the 6th. So this has a degree of 6. Crazy. All right. What about some not polynomial examples? I feel like this auditorium is so cold, my hands, like I can't write. Well, not that I really had good penmanship any other time, but I feel like they're just being a little stuck. I'm going to write this one as a capital F of x, just for the fun of it. I could have put a C, a D, an X, a Y, I just like capital F. Equals, I'm going to go -3, I'm stuck on -3s today, square root of x plus 2x squared plus 5. Sort of close to what it was up above. So this one's not a polynomial. If we go by our definition that our degrees or our exponents have to be positive integers. And what's this guy right here telling us? So anything that when you take the square root, this is the same thing as -3x to the 1/2 plus 2x squared plus 5. Right? So is our exponent a positive integer? It is not. It's positive, but it's not an integer, right? It's a fraction, or it's a rational number. So that is not a polynomial. And then if we threw g of x on there, let's say we had -3 over x squared plus the square root of 2x squared plus 5. So again, our integers are of our exponents have to be positive integers. So when I go by my exponent on my variable, well, is that positive? Because it says that it's x squared, right? But because it's in the denominator, right, we should bring it out of the denominator and put it in the numerator. So this is technically -3x to the -2 plus the square root of 2x squared plus 5. And so this clearly shows that our exponent is not a positive integer, it's a negative integer. So that one is also not a polynomial, right? When it came to our polynomials in our families, we kind of can come up with those families. So we're just going to call, oh boy, families. We are family, right? So you have constant functions. So a constant function would be if you had f of x equals some constant number, right? And we're going to say that c can't equal 0. Right? And then when it comes to this degree, well, there are no variables. So if there's no variables, the degree on that variable would be 0 because it doesn't exist, right? So those are your constant functions. Then we moved into linear functions. And so if we had f of x, probably the most common one would be mx plus b, that slope-intercept form, where our slope doesn't equal 0, because if our slope equaled 0, we'd be back up to a constant function. So our slope cannot equal 0, and it's a polynomial, and this would have a degree of 1. So anytime you are looking at linear functions, technically there is an exponent of 1 on that x, so you know that it's going to be a linear function. And then we got a little more fancy and we came up with quadratic functions. Let's say f of x, and you can write these a lot of different ways, but we're just going to stick with the standard form, right? ax squared plus bx plus c. And again, our a cannot equal 0, because if our a equaled 0, our x squared would go away, and then we'd be down to a linear function, right? And our quadratics always have a degree of 2. Right? So today, our focus is going to be on polynomials of degrees of 3 or higher. So we're going to look at some polynomials of degree 3 or higher. When we make our graphs of our polynomials, graphs of degree 2 or higher, we call them smooth and continuous. They need to be smooth and continuous, right? So what do we mean by that? So by smooth, we're saying that they have like rounded curves. Probably the easiest way to kind of think of it. And continuous, there's no breaks. Right? And we can't use this for, it has to be a degree of 2 or higher, because we can't do it for a linear, because on a linear looks, something like this, right? Where's those rounded curves? There are none, so. Alright. If I were to draw out something that looked like this, is it smooth? Yeah, because it has these rounded curves. They're not like absolute values, where absolute values gave you that V-shaped, right? They're nice and smooth. And is it continuous, where it has no breaks? Yep, it keeps on going. What if it looked something like that? Would that be a polynomial? Well, does it have rounded curves? Yeah, I'm rounded here, I'm rounded there. But do I have breaks? I do. Right here it shows that there is a break in the function or in the graph, so it is not a polynomial, right? Same thing if like we were just talking about, like absolute values. If I gave you a mountain, even a mountain and a hill and a valley, right? Well, because I'm not smooth, right? Not smooth there, then it's not going to be a polynomial. So we can look at graphs and we can tell if they are polynomials or not, and we can actually, when we look at the graphs, we can somewhat get a fairly good depiction on what the degree is on that polynomial as well. Oops. We can look at our leading coefficients, and our leading coefficients are going to tell us about what our end behaviors are going to look like. So our leading coefficients are the little guys out front, right? Because they're leading the polynomial. So the leading coefficient and end behaviors. Alright. So let's say we had f of x equals 2x squared plus 3x plus 2, right? And hopefully we know that this is a quadratic. It is a quadratic because it has a degree of 2, and my leading coefficient is also a 2. So when I think of my degree, I know that I have this, it has an even degree, right? Because my degree is 2. And anytime I have an even degree, my ends are going to go in the same direction. Right? And then on mine, since I have a positive leading coefficient, what do you think is going to happen? What's going to happen on the left side of my graph? My left is going to go up, right? Yep, so it's going to rise. And what's going to happen on the right side of my graph? Right? Yep, same thing. It's going to rise, right? This is going to go up. If we were to graph it, it would look something along this lines, right? Good job. What if we have, let's say, f of x equals negative 3x to the 4th plus 2x. So look at our degree. Our degree is even. So our ends are going to go in the same direction. My leading coefficient though now is negative. So I have a negative leading coefficient. So that tells me that the left side of my graph is going to go, yep, it's going to go down, so it's going to fall. And on my right side, since it's even, it's going to be the same thing, it's also going to fall. And when it comes to quadratics, or this 4th degree, hopefully we know that it's going to kind of go, it's probably going to look something like this, and it's going to go down, right? All right. Well, we don't always have even degree polynomials, do we? We could have negative degrees. So let's say we had f of x equals 4x to the 3rd minus 2x squared. So we know this is an odd degree. And if an even degree, the ends go in the same direction, what do you think odd degrees are going to do, the ends? The ends go opposite. Yep. Or we can just say, I'm running out of room a little bit. I'm just going to say opposite direction. Right? And then our leading coefficient is positive, so we have a positive leading coefficient, right? And if we don't know which way this goes, so we just, in the learning process of it, we could always use Desmos to put this into our calculator, and we can sit there and start making conjectures by putting in positive or negative leading coefficients with different degrees, and we can come up with a good little, the same exact table without me having to write it all out. But I do know that the left side is going to fall. It's going to go down, and the right side is going to rise. So in other words, if we were to graph this, I guess we could do on little graphs. Let's go back up. So an example like this, just cheesy example, right? This would have looked something along this lines. Right? This one, because it was negative, is going to look something along like this lines. This one, I am going to be falling on the left, so I'm going to start down, and I'm going to look, and I'm going to rise to the right. So that graph is going to look something like this. Right? We'll do the next one, and then I'll give you my cheesy analogy. And then, so we probably get one more example. So we need an example with a negative up front, right? So like a negative 3x to the 3rd plus 2x. So if we give all of our little explanations on this one, we know it's an odd degree. So our ends are going to go in opposite direction. Right. We have a negative leading coefficient. So that's going to tell us that on the left side, it's going to be just the opposite. We're going to rise, and on the right side, we are going to fall. Right. So, running out a little bit of room. But ultimately, this one will look something along this lines. Right? So, my cheesy example on these, I think when it comes to the even degrees, we're probably pretty good about knowing quadratics, or to the even degree, they're going to go in the same direction. And if it's positive, they go up. If it's negative, it goes down. It's just like in life, right? If you stay positive, you're going to go up, right? If you're going to be negative, you might as well just keep on going down. When it comes to the third degrees, I think of it kind of the same way. If this is to the odd and it's positive, no matter where life might be, you might be dragging you down, but if you continue to stay positive, eventually you'll end going up. If you're odd and it's a negative, you might be starting life on the up scale, going up. But if you continue to be negative, guess what's going to happen? You're going to end negative, right? So it really, if you know that your odds are opposite signs, and if it's positive, you know you're going to end up positive. If it's negative, you're going to end up negative. And then the other side is going to be just the opposite way of that. All right, we're going to talk about one more thing called zeros. And what these mean when it comes to our graphs. Zeros tell us like where they cross the x-intercept or the x-axis. So zeros are where the polynomial crosses the x-axis. Well, I guess I shouldn't say crosses. Could touch it as well. Maybe we should do hits. How about hits? Because hit could mean it goes through or across, maybe. We'll do it in. You always put it in quotes if you're not exactly sure like how to explain it, right? All right. So let's say we had a function f of x equals x to the third plus 3x squared minus x minus 3 equals 0. So we could go through by grouping, and we could actually factor this guy out. So just to save a little bit of time, I'm going to say that when we factor it, we're going to get x plus 3, and then you're going to get x squared minus 1 equals 0, right? And then if you want to solve these, right, zero product property says that either one or the other of these have to equal 0 if you're multiplying, right? Zero product property. If you're multiplying, one of them's got to be 0. So either x plus 3 has to equal 0 or x squared minus 1 has to equal 0. So this is going to give us x equals negative 3. This is going to give us x squared equals 1. So x is going to equal a positive or a negative 1, right? And we ended up coming up with how many solutions? We came up with 3 solutions. And they're telling us where we're going to cross the x-axis. So if I make my graph, 1, 2, 3, 4, 1, 2, 3, 4, I can get more and more accurate as time goes on with these, because this is telling me that I'm crossing at negative 3, negative 1, and at 1, right? I am a third degree polynomial, so I know my ends are going to go in opposite directions. and my leading coefficient is positive, and if my leading coefficient is positive, I know that I'm going to end going up, so that means my left has got to fall. So just doing a generic graph, I know then that I got to come up and I'm going to hit there. I somewhere have to turn and come back and cross my -1. And then I'm going to turn again. Whoops, kind of got a little wide. Turn again. Right? Granted, as time goes on, we're going to figure out our x-intercepts or our y-intercepts, and we can kind of figure out some more good little stuff on that. But when it comes to these, when we know that we have this thing called multiplicity. Multiplicity is like how many times it happens. And when I look at my roots or my zeros, I have a -3, I have a +1, and I have a -1. And the multiplicity of each one of those happening is 1. And since the multiplicity of them crossing is 1 or odd, we know that it's going to go through the x-axis. So what's an example of one that doesn't, right? So let's say we had f of x equals -x⁴ plus 4x⁴ minus 4x² equals 0, right? So we could go through, we can pull out a x², and we'll pull out a and then x minus 2² equals 0. So then I know that either x² has to equal 0 or my x minus 2² has to equal 0, right? So this x² equals 0, this is x times x. So really, x equals 0 or x equals 0. On this one, because it's squared, it'd be x minus 2 equals 0 or x minus 2 equals 0. Well, these two are solved for us. And this would give me what? X equals 2, and this one would give me x equals 2. Right? So on my graph, it's telling me that I'm going to cross when x equals 0. Oh, but then x equals 0 again, x equals 2, and x equals 2 again. So this has x equals 0 has a multiplicity of 2, right? Because I have it twice. These 2's have a multiplicity of 2 because it happens twice, right? So the multiplicity on these ones are even. Excuse me. So instead of going through the axes, I'm going to hit the axes twice. So if I look at my original equation, I'm to the 4th, so that means my ends are going to go in the same direction, and my leading coefficient is negative. So since my leading coefficient is negative, I know that my ends have to go down and down, right? So what happens when I graph this one, I'm coming up, right? And I'm going to hit that 0, this first x equals 0. And normally I would go through, but instead of going through, because I have this multiplicity of 0, it's almost like I hit it again. So I turn. Oop. And then when I turn, I still have to come back up at some point because I have to catch this 2. So I hit the 2, this first 2, but then it's almost like I have to hit it again. So it forces me to turn back around, and I go back down. So I kind of, if it's odd, if the multiplicity is odd, you go through the line, right? You go through the x-axis. if it's even, I call it touch and turn. Touch and turn, right? Because you came up and you touched it at 0 and then you turned. You came back up at 2, you touched it, and then you hit a turn and come back down. All right. Running out of room. Oh, I ran out of pages. I should just stop for today, huh? One quick one. So if you have f of x equaled to x minus 3 x plus 1 squared, right? And if you want to find out the zeros, so 0 equals 2 times x minus 3 times x plus 1 squared, right? 0 equals 2, that doesn't make any sense, right? 0 equals x minus 3, that's going to give you x equals 3. And then you have x plus 1 equals 0, but it's squared, right? So it's x plus 1 equals 0 again, where you have x equals -1 and x equals -1, right? So when it comes to your graph, you have x equals 3 and you have x equals -1. When it comes to your degree, you just got to make sure you're multiplying all of the x's. This guy is really x squared, right? And then you get another x, so it's x to the third. So it's odd, so they're going to go in opposite directions. And it's positive, the leading coefficient's positive, so you're going to end going up. So you're going to start down at the bottom. But when you come up and you hit -1, are you going to go through -1 or are you going to touch and turn? Yep, you're going to touch and turn. And you're going to go down, and somewhere or another you're going to come back up, and when you get to 3, are you going to touch and turn or go through? You're going to go through, right? So it doesn't have to, it's not one or the other for the problems. Each of those zeros has a different touch and turn or go through. Alright, I think that's enough for today.